Welcome to the Department of Computer Science and Engineering's Colloquium Series. I'm Larry Snyder, and today's speaker is Brad Chamberlain. It's always an honor and a pleasure to have alumni come back. Brad got his bachelor's degree at Stanford University and then came to UW and joined the ZPL project, where he was a major force behind the design and also behind the implementation. And he did actually so much stuff in grad school that his dissertation was 400 pages long, which I don't recommend. So after grad school, he was with the startup for a brief period and then went to Cray, where he heads the Chappaqua project. And Chappaqua is Cray's entrant in the competition for the next high-performance computing programming language. And I think maybe it's like the last language standing. So we'll hear about it today. So, Brad.
All right, thanks very much. So thanks very much, everybody, for coming, and congratulations on braving the snow, or surviving the snow, or whatever you want to call it, that caused this to be rescheduled. 400-page dissertation. Turns out it's really easy to write. Just use a really large font size, big margins, and lots of pictures. You fill up pages faster than you'd know it. So today I'm going to be talking about Chappaqua, which, as Larry said, is this language that we're developing at Cray. The title of my talk today is Parallel Programmability for HPC. I figure that now that Larry's retired, HPC may not be an acronym that's used as much in the department. So just to clarify, because I use it a lot, HPC stands for High Performance Computing, so really large computers, really lots of processors, lots of memory. And because a lot of you may not work in HPC, I'm also going to try to draw a relationship between what we're doing in Chappaqua and what you might need to be doing on your desktop in coming years. Okay? So if you're not familiar with Cray, Cray is a large company. We build supercomputers, which are these very large computers. These are some of the largest ones that we've built here. They have very nice panels on the front. If you've never been near a supercomputer, they're built out of these cabinets, which you can see a few standalone cabinets down in the bottom right there. These cabinets you can think of as being just like very, very large but narrow refrigerators. So once you put a whole bunch of them together, they fill rooms and consume a lot of power, make a lot of noise, get a lot of computation done. And so Cray's business is building these. My business is making them easier to program. I will mention that while these larger ones at the top are somewhat expensive, we are increasingly trying to market these smaller ones to universities. So if the department of the university is interested in buying one, please talk to me afterwards. Sure, we'll take money pretty much any way we can get it. So let's see. When you think about supercomputers like this, a lot of you might think about the top 500, which, if you're not familiar with it, is this competition that happens twice a year. The goal is to rank the 500 fastest computers in the world. Of course, it's the fastest 500 who bother competing. So if you have a really fast one and you're not entering, you might try. The way they measure these is using a benchmark called LinPack. And LinPack is essentially a dense LU factorization code. And the nature of the computation is such that your peak flops rate is really what's going to determine what puts you onto this list. So to some extent, the more peak flops you've got in your machine, the higher you're going to end up on the list. But the fact of the matter is, for real computations that our real users want to use in the field, there are a lot of other things that determine the performance that they're getting out of the machine, such as memory bandwidth, for example, for both local within a node and across the network. So something that we try to focus on more at Cray is, for real applications, what kind of performance is sustained for those applications over a long period of time, right? Taking into account the communication, the setup, the I/O, sort of everything that makes the system work well. And a few years ago, we broke the petaflop barrier on an application. So sustained petaflops on an application that was computing superconductive materials. And at that point, somebody went back and noted that for sustained application performance on a real application, Cray holds sort of the records in each of these. So we got the first gigaflop in '88. We got the first teraflop in '98. And so every 10 years, we sort of get to another 1,000 faster on a real application. So this means that we need to get to the next flop if this trend continues around 2018. We don't know what kind of Cray it'll be or quite how many processors it'll be, but it'll be a lot of them. Now, I'm a programming models person. When I see this slide that, again, Cray sort of put together for me, the question I asked was, well, how are all of these codes written? And so I went and did a little bit of research, and the answer I came up with was shown here in purple. So that first gigaflop was written using Fortran 77 plus Cray auto-tasking and vectorization, which are essentially compiler techniques for injecting parallelism into your code. Then when we moved to the teraflop, we had a pretty big change in the way we program these machines. So we started using this library called MPI, which is still dominant today. It stands for Message Passing Interface, and it's a way of communicating between distinct processes. So again, there's a phase change going on there, although Fortran was still the base language. And then for the Petaflop in 2008, some C++ crept in, some more modern programming language got into the mix. MPI was still the dominant model for the parallelism. There was also a little bit of vectorization on the node. But now as we look to an exaflop, what we're anticipating is there's going to be another one of these phase changes. So MPI has served us well over the last two system scales, but for the next one, we expect things to be different. And if you ask people to gamble on what it would be, the conservative answer would be some mix of C, C++, and Fortran, plus MPI for the internode concerns, but then increasingly using something else within a node. Maybe something that would drive an accelerator or a multi-core like CUDA, OpenCL, OpenMP, or OpenAC are sort of the main things people are looking at today. Okay? Or maybe it'll be something completely different. And this might be good because when you have to change, sometimes it's good to change something better. So I think there's a question up here at the top.
Sort of dropped out in the middle there in the 98.
Yeah, so in 98, if I recall correctly, this is before I worked at Cray, the processors here were essentially scalar processors, and so there wasn't a big need for vectorization there. For that gigaflop, Cray had a big business in vector processors. That was a lot of what they focused on. And then back with the petaflop again, we're seeing more and more vectorization on conventional processors, and so I think that's why it's starting to creep in again there. Yeah. Hank?
What's a processor?
What is a processor? That's an excellent question, and the definition changes over time. I try to avoid the word processor, so I tend to talk in terms of nodes, which are like the chunks of hardware that have to go across the network in order to talk to each other. And nodes used to be just a single processor, but now more and more they are a processor chip that has multiple processor cores. So I tend to use the words node and core rather than processor, because I think processor sort of, to some people, means one and some to the other. Yeah.
It's hard to know.
Then it gets really tricky for this processor count. Yeah, then this is a problem we're already running into where people just don't know quite what terminology to use because as you look at different system architectures, the terminology changes, and so it's hard to say how many processors did you use on your IBM versus me on my Cray. It's something I think the community is still very much wrestling with. But things that are pretty standard are talking about sockets, which is sort of where do you plug in the chip, and nodes, which is kind of where do you go across the network. And today, processor cores, although again, as you say with accelerators, I think even that definition starts to get a little more complicated. All right, so as I was saying, maybe it's time for something completely different. Now, it'd be great if I could tell you about these real applications in a lot of detail, but that takes a lot of time. So I'm going to go to the opposite end of the spectrum, take the sort of simplest parallel computation I can describe to you easily, and this will be a motivating example for this talk, and we'll come back to it a bit later in the talk. This is a benchmark called the stream triad benchmark. It's very simple. You basically have three vectors, A, B, and C, and you're going to take the vector C, multiply it by a scalar, add it to the vector B, assign it to the vector A. Okay? Now, this is a trivially parallel computation. To show it in pictures, if I divide up the vectors where these blue bars are, I can sort of chunk the work up, and if I'm running on a 4-core machine, for example, give each of those cores a quarter of the work, and there I have a parallel computation. Now, most of the Cray machines that we saw are large distributed memory machines. So there you might do the same decomposition of the work and the data, but you might end up replicating some data as well. Like here I've shown the replication of the scalar alpha, so that rather than going across the network to get that alpha, which is a constant, you can just have your own local copy and not have to do the communication. And then, as we were just discussing, more and more of these large distributed memory machines have multiple processor cores within each node, and so you might end up with these hybrids where you have sort of distributed memory parallelism and then shared memory parallelism within each node. Okay? So the way we would code this up today using MPI is some code here. I'm not going to walk you through it. You could probably not even see it, but hopefully you might be able to see on the left here there's some code in red. This is the MPI code. Again, this is sort of message passing types of thing. There's not much of it because this is such a simple computation, there's not much coordination that needs to be done across the processors. So it's basically set up and tear down. And then the code itself is here in the green. This is doing the vector multiply add. And the rest of the code is sort of set up and tear down initialization, things like that. And this code will give me the distributed memory parallel version of the code that I'm showing iconically up here at the top. Now, if I want to take care of the internode parallelism as well, I might mix in something else like OpenMP. OpenMP is a loop markup annotation. I can use this blue code here to say, hey, these loops are parallel. Please use whatever parallelism is available within the node in order to execute these loops. And then I have the hybrid parallelism that a lot of our machines have today. But then as I alluded to, more and more of these machines are looking at having more exotic things like accelerators in them. So then I might switch to something like CUDA in order to use those accelerators. Again, I'm not going to walk you through this in detail, but the purple code shows the CUDA constructs, ways in which the code is impacted by CUDA. And as you can see, it's fairly impactful. And if you were to look at this in detail, it's fairly different than what we're doing in MPI or in OpenMP. Okay, so I think the problem we have here is that HPC as a community suffers from having way too many distinct notations for expressing, in this case, a really, really trivial computation, and generally the same two concerns over and over again, just at different system scales. So programmers typically care about parallelism. What can I run in parallel, and how should I run it? And then locality, sort of where are these things running with respect to each other and with respect to the data. So the hypothesis is we should be able to do better than this, and then we wouldn't be having to change notations all the time. So a question you might ask is, well, why do we have so many of these different models? And I think the answer is that HPC has typically given the users programming models that are very close to the target hardware and reveal a lot of the capabilities of that hardware. And therefore, when the hardware changes, the programming models tend to have to change as well. So this is good in some ways. In particular, it gives the user lots of control, a decent amount of generality. If the hardware can do something, you can probably do it too. And these tend to be fairly easy to implement because they're fairly close to the hardware. But as you can see, the downside is that as you're targeting different types of hardware parallelism, or as you're trying to use different units of parallelism in the software that you're writing, you have to switch notations, right? So in the middle column here, I show all the different notations you might use for targeting different types of hardware or talking about different styles of parallelism. So this leads to the downsides. There tends to be lots and lots of user-managed detail in these programming models. We saw that in the colored code I showed in the previous slide. And the code tends to be fairly brittle to changes, both in the algorithm itself and the way it's mapped to the hardware. And therefore, as the hardware changes, the models have to change as well. All right? So at this point, again, assuming that most of you aren't working in HPC, you might be saying, well, I'm really glad I'm not an HPC programmer. Sounds like you guys have it really rough. I'm going to use a mainstream desktop, and so all this is just academic to me. Good for a talk, and then I'll go home. Unfortunately, I think the reality of the factor is that these things that we've been concerned about in HPC for decades now are sort of creeping more and more into the mainstream. Right? So already, you probably don't own a computer anymore that has just a single processor core in it. So already, if you're a performance-minded programmer, you might be thinking about parallelism, and you probably have to do more and more of that as time goes on, and you have more and more cores on your processor that you want to make good, effective use of. And I would argue that as our processor chips become more and more complex, as the number of cores increases, locality is going to become increasingly important as well, just because you can't just jam hundreds of processor cores onto a chip and expect it all to be kind of completely flat and completely oblivious to locality. All right, so that means the concerns of HPC are sort of coming down to the mainstream as well. And we can see this if we look at, in HPC, the next generation processor technologies that we're talking about building machines out of, things like the Intel MIC architecture, AMD Fusion, NVIDIA has an architecture called Echelon, and then Tilera is a company that has a tiled processor architecture. And these are the kinds of processors that we're talking about building our next generation machines out of. But again, these same technologies use the same kind of themes and concepts and technologies that I think are going to be showing up more and more in the mainstream. Okay? So what are these concepts? Well, one of them is that while these different designs are quite different from each other, all of them have an increased amount of hierarchy and or sensitivity to locality within the chip. You sort of need to make sure you know where your data lives and where it's flowing and try to worry about that if you care about performance. And the second is more and more of these chips are starting to introduce heterogeneous processor types. So we're talking about accelerators before and the fact you might have CUDA processor cores and then your normal CPU processor cores as well, and also different types of memory. Okay, so all of this means that both within HPC and in the mainstream, programmers have more and more to worry about as they go forward, performance-minded programmers anyway. All right, so jumping back a few slides, I sort of argued that HPC suffers from too many ways of talking about parallelism and locality, the two main things that we care about. So what I'm going to do, of course, since I'm a language person, is introduce yet another notation, right? So this is the Chappaqua code for that same stream triad benchmark. I'll walk you through it in detail a bit later in the talk. But mostly what I want you to take away at this point is it's fairly short, fairly succinct, and I would argue much more readable and understandable than the other notations we saw. Okay, so that's all well and good. But the other nice thing is that this Chappaqua code can run in any one of these modes we've talked about. It can be run as a serial code, multi-core parallel code, distributed memory code, or the combined distributed memory multi-core, as well as, in fact, many other variations as well. Okay, so how do we get away with this? Well, the secret is this dmapped clause here, which Dan Grossman would call the special sauce. And so this dmapped clause essentially says, here's how this index space and these vectors should be mapped down to the hardware, and here's how the parallelism should be implemented. And so by changing that dmapped clause, you can completely change the way in which this program is realized. Okay, we'll talk much more about this towards the end of the talk. But before I go on, I just want to say the philosophy here, the thesis of this talk, if you will, is that good programming language design can tease a lot of these details of locality and parallelism that in today's models tend to muck up your code away from the scientific algorithm you're trying to express itself. And that this permits the compiler, the runtime, the application scientist, and the parallel computing expert each to focus on the thing that they do best and not worry about all the other things. All right? So this is the outline for my talk. I've just given you a little bit of motivation for Chapel. Next, I'm going to talk a little bit about Chapel's background and some of the themes that motivate the language. Then I'm going to give you a really kind of rapid-fire tour of some of Chapel's main concepts. Not enough to make you experts, but hopefully enough to give you a sense of the language. And then I'll dive a bit deeper into a few of the research topics we've been looking at. And at the very end, I'll wrap up with a little bit about project status and where we're going. All right, so what is Chapel? As you've probably gathered by now, it's this emerging parallel programming language that we're developing at Cray. The design and development are led by Cray, but we've been working since the beginning in partnership with a number of collaborators in academia and national labs and a bit in industry as well. Chapel came out of a program that was sponsored by DARPA called HPCS. This stands for High Productivity Computing Systems. So the goal here was to stop focusing exclusively on performance and talk more about what would make people really productive on these large-scale machines. So the overall goal of Chapel and to an extent of the program is to improve programmer productivity. And in Chapel's case, we think of this as drastically increasing the programmability of these large-scale machines while still getting performance that matches or beats what you would get with conventional programming models today, improving the portability of programming models, especially as we go to new architectures like we're looking at going forward, and also improving the robustness of our parallel codes. The other thing you should know about Chapel is it's very much a work in progress. So this is ongoing work, and it's work that would benefit from feedback from the audience and collaborations going forward. So Chapel's implementation, it's worth saying, is being developed as an open source piece of software. The code is all hosted at SourceForge, so you can look over our shoulder on a day-to-day basis and watch our missteps as we go. It's licensed as BSD software, so it's very permissive if you're interested in using it. It targets Cray architectures, of course, but we've designed Chapel, both the language and its implementation, to be very portable. So in addition to Cray architectures, you can target multi-core desktops and laptops, commodity clusters, systems from Cray's competitors. And more we're looking at these new architectures coming out, CPU accelerator hybrids, many-core architectures, the kinds of things I showed a few slides ago. Now at this point in the talk, I usually talk about these motivating Chapel themes, which is sort of, if we had a blank sheet of paper, what allowed us to decide what should or should not go into the Chapel language design. But I didn't want to get bogged down in this too much today, so to save time, I'm just going to skip through and do every other theme. The others you'll sort of pick up on along the way. So the first theme here is support for general parallel programming. And this is an idea we've already touched on. The idea is that today, to target different types of hardware parallelism or to express different types of software parallelism, you typically have to use different programming models and then mix and match them if you want to get the whole spectrum of things. And so what we'd like to do is, with a single unified set of concepts, replace the middle column of this table here with Chapel, right? Use Chapel across the node, within the node, everywhere, right? And to make that all hang together well. That's the general parallel programming theme in a nutshell. If you can't do it in Chapel, then maybe we should be changing Chapel so you can, right? You should never get to a point where you say, well, that was fun while it lasted, and now I'm going to go back to MPI. All right, the third theme, or the second, I guess, today, is what we call this multi-resolution language design. And the motivation for this is, I've just been arguing to you that the models we use today are pretty low level, pretty close to the target architecture. And so I can do a lot with them, but at some point I find myself saying, you know, I'm writing the same idiom again, it's kind of painful, why do I have to take care of all this stuff myself? That's not the way that all programming models for HPC have been. A number of higher level models have been proposed over time, although none of them have really ever gained widespread adoption. So like in the 90s, there was a language called high performance Fortran that got a lot of attention. Here at UW, we were working on the ZPL language. And both these languages provided much higher level abstractions. And when they worked for you, you were very happy, and you were very removed from all the little details and fiddly things associated with running on parallel hardware. But at the same time, you were removed from the target architecture, and there was no real way to get closer to it. So when those abstractions failed you, you were kind of stranded, right? And so the idea behind this multi-resolution design is to fix this. And so what we're doing in Chapel is we have designed the language to have multiple tiers of features. Some of them are quite low level and close to the target hardware, so you get a lot of control out of them, but you are dealing with more details. And others are higher level and more abstract. And we're going to build those higher level features in terms of the lower level ones. Right? So they're all intercompatible, and you can move between these levels of language as your code or algorithm or performance warrants. All right? And this has worked very well for us. We'll hear a lot more about this later on in the talk. And then the last thing I'm going to talk about today is trying to reduce this gap that we think exists between the languages used in HPC and those used in mainstream computing. Right? So when I go and talk to students, my sense is that more and more students are coming out of school with training in things like Java, MATLAB, Perl, Python, these fairly modern and fairly productive languages compared to the things I was taught in. Yet then if we hire you into the HPC space, we say, well, here's Fortran, and here's C, and if you're lucky, here's C++, and here's this thing we called MPI. And I think a lot of students are just in for this culture shock. They feel like they've been teleported back 20 or 30 years. So with Chapel, we'd like to try to narrow this gulf, both to take advantage of progress in modern language design, bring some of those lessons learned into HPC, also be able to provide something that new students coming out can use more easily and leverage more of the skills they learned in school. And at the same time, we're trying to design it in a way that we don't ostracize the traditional HPC programmers. So if you're a Fortran 77 guy who's been in a lab for 40 years, we're not going to force you to learn object-oriented programming. There are objects in language. You can use object-oriented programming if you want to, but you can also avoid those and program in a very traditional imperative block-structured style if you want to. All right? So those are the language themes. Next, what I'm going to do is give you a tour of some Chapel concepts. And again, this is the kind of thing we could spend a day teaching you guys Chapel. We don't have a day. So this will be just kind of giving you a flavor of some different features in language, both to kind of give you a sense of what's in there and also to set up for our advanced topics at the end. And I'm going to do this by taking that language stack I showed before, and I'll sort of use that as our guidepost. So we'll start with the base language. You can think of the base language as being, if you took Chapel and you took out all the parallel constructs and all the locality-oriented constructs, that's what you'd be left with. It's essentially like the C or the Java of Chapel, if you will, except it's not either one of those languages. We started mostly from a blank slate, although we took a lot of lessons learned from other languages. So one of the things we have in Chapel is static type inference. So what this means is when you're writing your code, there are a lot of places where you can leave off type declarations, and the compiler will fill them in for you. So this is a lot like a scripting language, except that the compiler is still figuring out the types, and you're not paying the runtime overhead for dynamic typing and things like that. And so just to give you some quick examples, in the top section of code here, I declare a number of constants, and I'm not declaring the types of them, although I could. So what happens is the compiler looks at the initializing expression. It sees, for example, that 3.14 is a real floating point literal in the language, so it infers that pi is a floating point constant. Similarly, it sees the string Brad here, and it infers that name is a string. This type inference also applies to things like procedures and classes. So I can leave off the argument types of my procedures here, the return type, and what I've ended up doing is written a very generic procedure here that I can call with different type signatures. And this gives me kind of a template style mechanism like in C++. So if I call this with an integer and a real floating point number, I'm going to get a real floating point number out. If I call it with two strings, well, plus means string concatenation in Chapel, so I'll get a string out. Yeah, question up top.
So are the generics like the templates in C++ and that they're always specialized, or do you actually have generics?
Today, the templates are specialized, so we actually do stamp out multiple copies of the code. Another thing that's in the base language is these range types. A range is essentially an integer sequence. Like this range literal up here means the number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have a number of operators on ranges which create sort of an algebra for ranges. So we can do things like select off a subset of the number of elements from a range, or we can stride a range, or set its alignment. And to a language minimalist, this may seem kind of sugary, right? You don't really need this baked into your language. But in HPC, when you're dealing with a lot of large multidimensional index spaces, having this and the nice syntax for it is something that ends up making people much more productive. And we get a lot of positive feedback from users for these kind of features. Then we have iterators in the language. Iterators are like functions that rather than returning a single time, they yield values, and you can use these to drive for loops. You may have seen these in Clue if you're sort of an academic, or more recently, I think Ruby and C# tend to have these style of iterators as well. So this first iterator is a Fibonacci iterator, takes in an integer n, and it'll return that many Fibonacci numbers. So I can use it to drive a loop, as I've shown here. This loop says basically iterate over the first 7 Fibonacci numbers and print them out, and that's what's going to happen. A more realistic example, this is a tiled row major order iterator. So it does a tiled iteration of a multidimensional index space. And this is something that if you do it manually in your code, it ends up with a lot of loop nests, a lot of little details that clutters up your code. The iterator is a nice way to put it into a procedure, essentially, that can be parameterized by things like the tile size, and then invoke it within your code in a much more clean way. And then the last base language feature I'm going to talk about is zippered iteration. This is the notion of iterating over multiple things in kind of a lockstep or a zippered manner. So here I'm iterating over a range with n elements in it and my Fibonacci sequence, or my Fibonacci iterator, and I'll print those out. And so I get the corresponding elements of the range, like 0 is the first element in the range, and the corresponding Fibonacci number. So 0 is the first Fibonacci number as well. All right. And there are lots and lots of other base language features, of course. I've got a list of some of them here. I won't march you through them, but I will make these slides available for people to look at offline afterwards if they'd like. So let's move on to a different level of language, the task parallel level. So task parallelism is a way in Chapel of saying, I'd like to do this computation while some other task is doing this other computation. And we have a few ways of introducing them. One of them is a co-for-all loop. This is like the serial for loop we just saw, except that it creates a distinct task for each iteration of the loop. So in this case, I have a loop that goes from 0 to my number of tasks, and I'm going to just print out a little message from each task. And because I'll have a separate task for each iteration, these messages might come out in any arbitrary order. The one thing I'm guaranteed in the co-for-all loop is that the main task that entered this loop will not continue until all the child tasks have completed. So this write line, all tasks done, is guaranteed not to complete until all my other messages have been printed out. Okay, so this is a concise way to introduce a bunch of tasks that are doing more or less the same thing. A second style of introducing tasks is this co-begin statement. And I'm using in this slide to do a bounded buffer producer-consumer example. Okay, so I use this co-begin, which is a compound statement. And what's going to happen is each of the child statements in that compound statement is going to be in a separate task. So in this case, I have one task that will execute this producer routine, and a second task that will execute the consumer routine. And then there's an implicit join here, as there was with the co-for-all loop. The other thing I use in this example is an array of these synchronized real floating point variables. A sync variable in Chapel is essentially a normal variable, so this will store a floating point value. But then it also stores an extra bit of information we call the full empty bit. And so reads of this variable are going to block until that bit is set to full, and it'll leave it empty. And writes are going to block until the variable is empty and leave it full. And what this allows me to do is write arguably the most elegant producer-consumer you could. I basically have the producer and consumer routines just going in a loop, reading to or writing from this array. And those full empty semantics take care of all the normal problems of a producer getting ahead of itself or a consumer getting ahead of the producer. Because the full empty bits manage all of the synchronization in a data-driven way. Okay. So those are some of the task parallel concepts in language. Next, we'll move on to locality, which is in many respects the lowest level of language. It's the closest to the target machine. And the main feature we have for locality is this type in language called a locale. You can think of the locale as being an abstract type that represents some subset of the parallel hardware in which you're running. And for each parallel hardware, it's mapped to a piece of that hardware that's useful for reasoning about locality. Essentially, anything within a locale should be here and close and fairly cheap to access. And anything in a different locale is still accessible, but at some cost, right? Typically, you have to go over a network or something like that. So in most conventional processors, these locales are mapped to a node. So typically, a multi-core processor or an SMP node of multi-core processors. And we really don't say much more about these locales other than that they can run tasks and they can store variables, which means they have some sort of processor capability, maybe an accelerator, maybe a CPU, and they have some kind of memory. All right, so how to use these locales? When you run your Chapel program, you can specify in the command line how many locales you want to run on. In a sense, this is a way of saying to the machine, this is how many resources I'd like from you as I'm executing this program. So in these command lines here, for example, I'm requesting 8 locales. And then built into the Chapel, there are a couple variables you can use to refer to the machine resources you've been given. So one of them is just an integer called num_locales. In this program execution, it would be set to 8, and I can reason about the fact that, OK, I've got 8 locales to run on. And then you also have this array that's built in that's an array of locale types. And you can think of this array as being a way of referring to the machine resources on which I'm running, right? If I'm running in 8 locales, the array will have 8 elements, and each of those elements will correspond to, for example, a node in my large Cray system. All right, now what do you do with these locales? One of the things you can do is locale type supports a number of queries, which allow you to reason about the machine resources on which you're running. So there are queries that allow you to do things like ask, how much physical memory does this locale have? Or how many processor cores does it have? And this kind of gets back to Hank's question. We call this num cores because at the era we were developing these, processor core was a good term. But as you're getting onto something like CPU-GPU combination, what should the answer to this be? Or really the question is, what should we evolve this interface to be in order to let you introspect about that kind of hardware? You can also ask things like, what's the unique ID of this locale, or what's its name? And the other way you use locales at this low level is that we have these on clauses, which essentially say, execute this computation on this specific locale. Okay, so this first example is very simple. I start running the program on locale 0. I print something out. I then use this on clause and say, now go run on locale 1, print something else out. And then when I leave that on clause, I'll return back to locale 0 again. Okay, so this is just a way of moving computation or data to specific machine resources on the target machine, again, in a very low-level manner. It's important to note that these on clauses are completely orthogonal to parallelism. So I can use these in conjunction with the task parallel features we saw before. For example, I can use a cobegin here to say create 2 tasks, and I can use the on clause to tell those tasks where they should go run. And I can also do this in a data-driven manner. So this first on clause says, go do this big computation wherever element ij of this array lives. Okay, I don't know where it lives, just go find it and execute there. Or the second one, maybe I'm walking a tree and I say, wherever the left child of my node is, go execute this task there. All right. And those are the low-level locality features of the language. Fortunately, you can often program at higher levels. These data parallel features we'll talk about next. So the data parallel features are all based around this concept of domains. This is a concept that came out of the ZPL work we were doing here in the 90s at University of Washington. Domain is essentially an index set. So you can think of it as being like the size and shape of an array, but there's no actual data associated with it. And you use these both for creating arrays and also for doing things like defining iteration spaces. And so Chappaqua has a number of different kinds of domains. We have dense rectilinear domains, strided variations of those, and then we have sparse domains, which can have an arbitrary subset of indices from some other parent domain. We also have associative domains, which are essentially sets of values you can use to create hash tables and dictionary-like data structures. And then we have these unstructured domains that are designed to support more pointer-based data structures that don't have sort of well-defined names for all of their members. And each of these domain types can be used to create arrays. So arrays are essentially mapping from the indices in these index sets to some sort of element type and variable of that element type. And then each of these arrays supports a number of different operations. And I'll walk you through some sample operations just in the dense rectilinear domain, although the same kinds of things apply to the other types as well. So all of our domains and arrays support for all loops. This is a way of saying, for every index in this domain or for every element in this array, do some computation. We also have things like array slicing that allow you to refer to subsets of arrays using domains as index sets. And then we have promotion of scalar operators and functions. So for example, the plus and times operator in the language are really only defined on scalar values, but you can call those with array arguments, and the scalar operator is essentially promoted across all of the elements of the array. Similarly, if you write your own function, you can promote the function's scalar arguments across arrays as well. And there are a lot of other data parallel operators that we won't be getting into today, sort of anything you might want to do to manipulate arrays or reason about them. Just a couple notes on these for all loops to kind of set me up for my next section before we go on. So we've talked about 3 kinds of loops: for loops, which are serial; co-for all loops, which create a task per iteration; and for all loops are kind of somewhere in the middle there. Typically, they'll use a number of tasks that's proportional to the amount of hardware parallelism available. So usually a lot less than the number of iterations. And we'll talk more about this a bit later. And the other thing to note is that these for all loops can be zippered much like for loops can be. So I can iterate over, for example, this one-dimensional array and this range in a zippered manner. And even though it's happening in parallel, I'm still guaranteed that the matching elements are going to match up in the body of my loop. We'll talk more about that later on, too. All right, so that takes me to kind of the research side of my talk. I'll talk about a few advanced Chapel topics and the work we've been doing in this area. So the first of these is called domain maps. And here's some motivating questions that lead us to look at domain maps. So when I talk to users about these data parallel features you've just heard about, any user who cares a lot about performance is going to have some questions that they're going to come up with immediately. So one of them is things like, how are these arrays stored in memory? Like the regular arrays, are they stored in row major order or column major order, or maybe using some sort of space-filling curve or some sort of tiled allocation? And you mentioned these sparse arrays. So are the sparse arrays, do they use a coordinate data structure or a compressed sparse row or some sort of blocked sparse data structure, or any one of a number of things that people have been using in the community over the years? And a second question people might ask are, how are the arrays actually stored on these locales that I'm executing on? Are they completely local to a single locale, or are they divided up across the locales in some way? And if they are divided up in some way, are they blocked? Is it done in a cyclic manner, block cyclic, some sort of recursive bisection? Are they dynamically rebalanced under the covers? How do we actually divide things up? And the answer to all of these questions is essentially that any of these could be the answer. So Chapel very intentionally does not lock an implementation of an array into the language, but it provides this highest level feature, the domain map, as a means to specify how the array should be stored in memory, how they should be stored across multiple memories, like the multiple locales. All right, so that's what this section of the talk is about. So let's walk through that stream code in Chapel in a bit more detail than we were able to before. And now you know some of these concepts. I start out by declaring a domain, again, this index set, and it says that I'm going to be working on the indices 1 through m. And then I use that domain to declare my 3 vectors for the stream triad benchmark. So I say variables a, b, and c, their size and shape should be defined by the problem space domain, and I'm going to allocate a real floating point value for each index in that domain. Okay, so now I've got some actual data to compute on. And then I can use those promoted operators to say a equals b plus alpha times c. I didn't mention, but the promotion automatically gives you parallel semantics. So I've written this in a way that could conceivably be run in parallel. Now, if I just type the code like this and run it, I haven't said anything about how this domain is implemented or how its arrays are implemented. So what the implementation is going to do is it uses a default domain map. And the default domain map says, by default, all of these domain indices and its arrays elements are going to be allocated on the current local locale, the one that's running this code. And any computation over it's going to be executed using the local processors on that locale. Okay, so just writing the code like this, I essentially have a multi-core parallel code that would run using all of the processor cores of this Mac laptop, for example. All right, now if I want to change that, what I'm going to do is go into this domain declaration, and I'm going to add one of these dmapped clauses that I alluded to at the beginning of the talk. And so, for example, I might say, well, let's implement this problem space using the block distribution. And the block distribution takes some arguments. It takes a bounding box, which says, what part of the index space should I use in blocking things up? So I say the bounding box is 1 through m. That implies a partitioning on the one-dimensional set of indices, a partitioning on the domain that I've declared here, and a partitioning on the arrays as well. So now I've changed this computation from a shared memory multi-core computation to one of these distributed memory hybrid computations. Each locale is going to own a subset of the arrays. It's going to compute on those arrays, and it's going to compute using all of the processor cores within the locale by default. All right, so now I have one of these hybrid parallel codes I wanted. Now maybe I've got a code where a block distribution isn't really the right thing. I want to change something else. Well, I can change to a cyclic distribution, for example. It's parameterized by a start index, and then it just deals out indices in a round-robin manner across all the locales. And so I end up with this round-robin partitioning of my domain and my array. Again, I'm going to use multiple processor cores within each locale. And so I've completely changed the implementation just by changing this one little declaration saying, how should this domain and its arrays be implemented? And this is the kind of way that I mentioned at the beginning of the talk. We try to separate the algorithm that the scientists are trying to express down here at the bottom from the implementation details here at the top. Okay. So these domain maps you can think of as essentially being recipes. They say, how does the compiler take a high-level view of my computation, like this a equals b plus alpha times c, and map it down to the individual nodes and processor cores and memories that ultimately are going to have to execute this thing. And in a sense, the compiler is actually just sort of taking these high-level constructs and compiling them down to an interface that's defined by these domain maps. I'll just mention in passing that all of our Chapel domain types support these domain maps. So for example, for these unstructured domains and arrays, you might use a graph partitioning algorithm to divide that up across your locales. For associative domains and arrays, you might use different hash functions to hash the values across your locales. And so next I want to talk about Chapel's domain map philosophy. So this is sort of what guides our research here. The first bullet is a simple one. Chapel, when you download it and start using it, it should come with a standard library of domain maps. Right? So things like block and cyclic that we've seen are just kind of part and parcel of the Chapel distribution. You can just start using those out of the box. The second piece is that an advanced user ought to be able to write their own domain map. Okay, so if we haven't anticipated some exotic data structure or implementation that might be really beneficial for your code or your algorithm, that's something you can implement yourself. And in fact, you implement it in Chapel. So this is part of the multi-resolution scheme. The domain maps are the top, highest level feature in the language, and you typically write those using all of the lower level features, data parallelism, task parallelism, the base language features, and locality control. And then the third and sort of crucial part of this philosophy is that all of these standard domain maps that we're going to supply to you, we're going to write using the same mechanism that you would as an end user. And this is basically to keep ourselves honest, right? If I sort of built a bunch of things into the compiler, you can imagine the performance would be great. And the first time you write your own, you fall off a cliff and you can never get the performance back again. So to keep ourselves honest, we're sort of creating these domain maps in a way that they're good enough for us to do the built-in ones using the same mechanism that you would use as an end user. And I'm not going to walk you through a great bit of detail about how you implement these things, but just at a high level, what you're going to do as a user who's writing one of these is you implement 3 descriptors. They're implemented in classes in practice today. And these descriptors represent the domain map itself conceptually, like the block distribution, one of the domains that's allocated over those domain map, or one of the arrays that's allocated over those arrays. And so there's a standard interface you supply for each of these classes that the compiler is going to target as it's rewriting the high-level code down into your lower-level code. So if you supply these classes, you supply the interfaces, you've got a domain map, and you've implemented your own parallel distributed array. You can use the same high-level syntax that we saw at the beginning. Okay. I don't have a lot of performance results in this talk today, but here's one quick one. We've seen the stream triad benchmark a few times in this talk. And so this shows 3 versions of the stream triad benchmark. One of them is in green, and it's written using MPI, so that's the code we saw at the beginning of the talk. The other 2 are both written in Chapel. One of them is an embarrassingly parallel version that's very similar to the MPI. It essentially takes the parallelism across the nodes, and it takes it out of the timed loop. So each node basically is allocating a local vector and doing the stream triad over that local vector. So this is basically a test of local memory bandwidth. And this would only use a domain map that sort of targeted a single local domain. And as you can see, the performance there, higher is better on this graph, basically scales identically to the MPI. Right? So this says we can use these domain maps for sort of intranode concerns without a big performance hit. And then in the darker blue here is a different version. This is the global version. This is the version I've been showing on my code. And again, this is a distributed memory version where that creation of parallelism across the nodes is now within the timed loop. And so the reason it falls off a little bit is it takes a little bit of time just to sort of fire up all the parallelism across the network and then collapse it down again at the end of the loop. All right, so as you would expect, as the number of cores increases, the amount of time to fire off that parallelism also increases, and you lose a little bit of performance. But you have a great productivity advantage. All right, so if you're interested in more about these domain maps, we have a couple papers on them. The most recently was published in CUG this past year, and both these are available on our website. If you download the Chapel release and try using it, there's a technical note I've pointed to here which talks about how do you implement your own domain map. And as I mentioned, all of our own arrays and domains are implemented using the same mechanism. So you can dig through the code and actually see how we've implemented a number of the standard domain maps that come with it. And I guess it's worth noting that in Chapel, all these different domain and array types we talk about are all ultimately built on top of, there's sort of a single bootstrapped array that's built in, which is like a C one-dimensional array. And all the other domains and arrays are built within Chapel on top of that one concept. All right, so we have some next steps with these domain maps. Most of the domain maps I've shown you today are very static, very simple, things like this block and cyclic domain maps. But there's nothing about the interface itself that requires them to have that nature. So as long as you tell me things like, how do I iterate over the arrays of the elements of your array, or how do I randomly access your array, you can do really whatever you want under the covers. And so we think there's some really interesting things you can do. We just haven't gotten there yet. So one of them is you could have a domain map that dynamically load balanced, say, the data or the computation under the covers. You still say for all elements in this array, and under the covers it might move data around or move computation around to sort of reflect computational load on the machine. We also talk about using those domain maps to create resilient data structures, where maybe you're going to execute multiple copies of the iterations in case one of them fails, or you might store redundant copies of your data in case some of your memories go away or something like that. We also talk about using them to interoperate with legacy codes as a means of describing how data in your MPI program is laid out so that you can refer to it without redistributing it. And we also talk about using these for out-of-core computations, essentially using disks and files in place of the memory and the locales that we're targeting today, just as a different way of talking about your data that's off on disk. In addition to that, we still have a lot of compiler optimization we need to do, particularly for really well-structured communication idioms like stencils and reductions. This is an area we spent a lot of time in here at University of Washington and ZPL in the 90s. We haven't recreated all that work in Chapel, and that's work we have ahead of us still. All right, so next I want to move on to my second research topic, which is these things we call leader-follower iterators. And again, I'll start with some motivating questions about why are we looking at these things. So I talked about these for all loops, and I said that they use some number of tasks, typically between 1 and the number of iterations. And so again, when you're a performance-minded programmer and you care about how your program's going to execute, you might want to know, well, how many tasks are executing and where are they going to execute? And maybe more importantly, this array or iteration space I'm iterating over, how are those elements going to be divided up across all of my tasks? And another question you might ask is, I mentioned we have these, parallel zippered for all loops. And so there's a question about, well, how are those implemented? Like, how are the matching iterations going to be matched up to one another? Particularly if given that the arrays can have completely different distributions, completely different memory layouts, maybe completely different parallelization strategies, how do we arbitrate between all of these different potential array representations in order to implement these for all loops? Okay? And so leader-follower iterators are the concept that are designed to answer these questions. So Chapel's language semantics say that whenever you have a for all loop, one of the things you're iterating over is identified as a leader. It's typically the first thing in a zippering. So this A array, for example, would be the leader in this zippered iteration. And then all of the things you're iterating over are identified as followers. And the leader is essentially responsible for is responsible for determining how much parallelism should we use, and all the tasks executing that parallelism, what portion of the iteration space do they own. And the follower iterators kind of have no say in that matter. They're basically just given a chunk of work, and they sort of march to the leader's beat, right? Iterate over this subset of the larger iteration space, please. Okay, so what the Chappaqua compiler is going to do conceptually is take this this zippered for all loop here and convert it into this code in purple down here. So we're going to invoke the leader iterator. Again, that's going to create a bunch of tasks using the task parallel features in the language. And each of those tasks is going to yield some work. And then the follower iterators are going to accept that work as their input. And then using a normal serial zippered for loop, we're just going to march through those followers. And that sort of guarantees, again, that the like indexed elements are going to line up with one another. All right, so again, these leader-follower iterators are going to be implemented using multi-resolution features in the language. So the block arrays leader that I showed you before, for example, it looks something like this. We use a co-for-all loop to create a task for each of the locales that we're blocked across. And then we use an on clause to move that task to the specific locale. And then we use a second co-for-all loop to, say, create a task per processor core within this locale. And then we compute some piece of work as a function of our locale ID and our task ID. And we yield that back out. And then the follower iterator is going to take that work in as its input argument, and it's just going to march through that work sequentially, yielding the corresponding elements. Okay, so again, all of this is expressed within the language using the lower level features in the language, and this is what permits the data parallelism and the task parallelism all to completely interoperate with one another. All right, so some questions you might have, or a question, I guess. So what if I'm doing one of these zippered iterations, and I don't really like the policy that a leader iterator is using, or I want to change it? What are my options? Well, so one simple thing you could do is you could make something else the leader, right? Just by shuffling the order of the things you're iterating over. Again, the first one in any zippering is the leader, and so make something else the leader if you like its policy better. The second thing you can do is you can change the domain map of your domain or your array that you're iterating over. And each of these domain maps has a leader-follower iterator built in, so when I change like the block cyclic distribution, for example, I'm changing to a different parallelization strategy for all of its for-all loops. And then sort of the last resort is you can invoke a standalone leader iterator, sort of written as a standalone procedure. And so here, for example, I've shown I could call this dynamic iterator and say, well, please dynamically iterate over this array A, dealing out a chunk size of 64 to each of the tasks. And so that's a way of overriding all the built-in leader-follower iterators. So let's see, when we did some performance experiments with this, this graph shows for a number of different workloads on the bottom, for either 16 or 32 processor cores, how 3 different implementations of a loop compared. The base implementation is just a simple static blocking, what Chapel does by default. The blue is a guided schedule in Chapel, so it's written using this leader-follower framework, and it's a more dynamic and adaptive way of iterating. And then the orange is the exact same schedule in OpenMP, which is built into the compiler and built into the language there. So the main thing I want you to take away from this is that even though we're implementing these leader-follower iterators in Chapel, we can generate the same kinds of schedules as are built into things like OpenMP and get pretty competitive performance with OpenMP. But the other thing we can do is, because this is not baked into the compiler and the language, because you can specify these yourself, you can create things that aren't necessarily available in other languages. So for example, in this slide, we wrote an adaptive work-stealing leader-follower iterator, and we compared that against OpenMP's guided. Now, OpenMP doesn't have an adaptive, so we couldn't do an apples-to-apples comparison. And this just shows the flexibility of, by not baking these things into your language, you as a user can come along and create your own schedules and heuristics for executing these parallel loops. All right, so for more information on these leader-follower iterators, we had a paper at the PGAS workshop this past fall, and that's a good summary and introduction to what we're doing there. Within the release, there's a Premier example you can look at, which shows how to write your own. And there's also a standard module built in that has some of these dynamic load balancing iterators that I mentioned in the last couple slides. All right, so to summarize this section of the talk, both the domain maps and the leader-follower iterators, I think the important thing I want you to take away from it is that we've tried very hard in Chapel not to lock these very important decisions into the language, things that really affect performance a lot. Right? Instead, what we've tried to do is give you, the user, the ability to write them yourself within the language, and to be able to swap between different domain maps or different leader-follower iterator schemes with very minimal changes to your code. So you don't affect all of the science, and you're just affecting some of the policies as how it's to implement it. And again, we think that this really separates well sort of the application scientist who just wants to talk about their algorithm and the parallel expert who has to worry about mapping it down to the system, and then the kinds of things that a compiler and runtime can do for you. The last little bit I want to do in wrapping up is just talk a little bit about project status, and we'll take a few questions. So as I mentioned, Chapel's available open source. We tend to do releases about every 6 months. The last one we did was in October. And today where we are is that most of the features you've heard about today work at a functional level. So all these things I've talked about, you can run in parallel on your Mac or across a network of Macs or whatever you want, your Cray. There are many performance optimizations that remain. We focus primarily on functionality and correctness first to kind of see if the users like the concepts we're doing, and we're still working on tuning them and making them go faster. So this is a really good time to try out the language and compiler. If you have something that's not performance critical, you could use it for that. Definitely give us your feedback. It's not too late to improve things if we're off base in some way. I also think this is a great time to use Chapel for parallel education. So I haven't taught a class in a long time, and I don't think I've ever taught a parallel programming class. But if I were to, there's a bunch of stuff I'd want to cover. Data parallelism, task parallelism, synchronization, deadlock, live lock, performance tuning. And frankly, I think if I were to teach this today, there isn't really a good language for teaching all of these concepts, right? If you only want to teach your students one language. And in fact, some of these concepts, I don't think any languages we have today really teach all that well at all. But we really think that Chapel does a really good job of spanning this space well, again, because of the general parallel programming we're trying to provide. And we think it's a really easy language for students to pick up. So we're really encouraging educators to look at it. And we've had a few early adopters who've really had positive experiences about it. So there's a web page here and a mailing list. If you're interested in that, we can put you in contact with other educators that are using it or help you out ourselves. Again, Chapel's an open source and collaborative effort, so there are a lot of ways you can work with us. We have a small team at Cray here in downtown Seattle. We have a few open positions currently, so you can apply for those. We have a number of external collaborators, as I mentioned. And we also have an intern program. Every summer we have an intern or two. So if you or a friend or student or colleague you think would be a good fit for any of these kinds of roles, please send them our way. I'm not going to march you through this slide in detail. These are a number of the collaborations we have going on right now. They span a lot of different topics, many of which we wouldn't be able to get to within our core team ourselves. And again, they span academia and national labs and industry. So if there are people here interested in collaborating, we'd definitely be interested in hearing from you. And then I have a list of collaboration ideas, or rather areas where we could use more expertise or just don't have the cycles to explore. This is available on our website as well. So if you're looking for a project, either for a short-term thing or for a thesis, you might look through this and see if something resonates with you, and again, it might be a good area for collaboration. So to summarize my talk, I believe, and our group believes strongly, that these higher-level programming models can really go a long way in insulating the science that scientists want to get done from all of the nitty-gritty details of mapping it onto a real parallel machine that you have to do if you're running on these large-scale machines. And again, more and more on desktop machines. In Chapel, we think you can do this without abdicating all of your control, and we do this through this multi-resolution design I've been talking about, which allows you to do things like control how your arrays are laid out, how your parallel loops are executed, things like that. We think strongly that Chapel has a strong role to play for improving productivity, both for high-end HPC users and also, as I mentioned, increasingly for people on the desktop who are going to be able to, we're going to have to wrestle with issues of parallelism and locality going forward. We have a lot of work ahead of us, but I just wanted to call out a few things. One of the main ones we're looking at currently is this notion of hierarchical locales. So the locales I described today, as you saw, we have sort of a flat array of them. You can think of this as being sort of representing the horizontal locality on large machines, sort of when do you have to go across a network. But as I mentioned, the processor designs of the future are increasingly becoming hierarchical and heterogeneous. And so more and more you need to talk about vertical locality within a node as well. Which processor am I running on, or which memory am I storing this on, and what's its relationship to the other ones in the node. So we're talking about putting locales within locales as a means of expressing that still in a high-level way. But there's some big challenges here, like portability. If the locale structure of one machine doesn't match another, how much of my code do I have to change to move from one machine to the other? And will this multi-resolution philosophy save us from those kinds of changes? I mentioned we have a lot of performance optimization still to do. Generally speaking, Chapel is a sort of research prototype today. We do have real users who want to use it, so we need to increasingly work on taking it to a production-grade compiler. And the funding that we've been doing this work under comes to an end this fall. So the other thing we're working on as far as the next step is trying to figure out what's the future for Chapel after HPCS, what are the possible funding revenues and models going to be, and how will we keep it going. All right, so if you want more information about Chapel after today, we have a couple websites. One is chapel.cray.com. This is sort of the high-level information, things like papers, presentations. These slides will show up there before long. And then we have a lower-level page, which is where we host our source code. We have a number of mailing lists hosted there as well. You can download the releases from there. And again, that's a SourceForge website. And there are a number of mailing lists. The ones in green here are ones you might subscribe to. They're kind of community mailing lists. So ones for users or for educators using Chapel. And there are a number of other mailing lists that the team staffs for people to ask questions or report bugs on. And that's my talk. So thanks again for having me. Thanks to Carl and Larry for hosting me. Thanks again for having me.